So in this video, we are going to be, excuse me, talking about transformations of functions, but we're focusing on vertical stretches and compressions. Excuse me. So let's take a look at the vocabulary first right here in this blue box and make sure that we understand what the equation is going to look like and what the a value is going to represent. Excuse me. So we are starting with the function f of x, and we will end up with a new function, a times f of x, where a is a constant. Remember, that's just a number, and that constant is going to represent a vertical stretch or a vertical compression for that function. So here's when you know if you have a stretch or a compression. If the a value, oops, I'm going to color code this to match the graph over here to the right. So if the a value is larger than 1, so take a look at this a value is 2. Notice what it does to the graph. It kind of stretches it there. So that is going to represent a stretch. If a is going to be a number between 0 and 1, which would indicate a fraction, so a is between 0 and 1, then the graph's going to be compressed. So we can take a look over here and see that you're compressing it, you're shortening it. And so the other thing to keep in mind is, well, if a is negative, then that means there's going to be a combination of either a vertical stretch or a compression with whatever the value of a is, but it's going to also contain a vertical reflection, right? So that's what the a is negative. So let's take a look from a graphical perspective and see what we can do to graph a vertical stretch or compression. So what we have here is a scientist is comparing the population to another population whose growth follows the same pattern, but is twice as large. Okay, so this keyword right here is going to indicate that you are going to be twice as large. So you're going to be multiplying everything by a factor of 2. All right, so 2 times as large. So what you want to always do is to start identifying key points on the graph. And the key points are going to be wherever the graph changes shape. So let's take a look at this first point, which would be 0, 1. And then the next one, let's just make the math easy. Let's just call it 4, 3. 6, 2, and then 7, 0. Okay, we're just going to go with easier numbers right now. So remember that on a vertical vertical stretch or compression, the only thing that's going to change, the only thing that is affected is the y value. So the y value is affected, and it's affected by 2 times that. So all of your x's are going to stay the same. So there's no change in the x coordinates, but all of your y values are going to be multiplied by 2. So 3 times 2 is going to give me a 6, 2 times 2 is going to give me a 4, and 0 times 2 is going to give me a 0. So then you just plot those points, and then you are going to follow the same shape of the original graph. And there you have where you've just graphed that vertical stretch. So now we're going to take a look at what if I give you an already existing graph and you're supposed to determine whether it's a vertical stretch or compression. So the first thing that you want to do here is to identify your parent function. So your parent function is x cubed. So I'm hoping that you guys can see that that's the x cubed. And then the next thing you want to do, and I'm just going to move this over, is to look at g of x. And basically, we've taken that parent function and we're multiplying it by some a value. And then a times f of x, right? So f of x is that parent. So we've got to find the a value. So the best way to approach this is to find a nice point on the graph that intersects clearly. I would recommend staying away from 0, 0 because when you're multiplying anything by 0, you're going to get 0. But we can definitely use that 0, 0 point later to kind of check. But for right now, I'm going to look at that point and say that's 2, 2. So over here on the graph of g of x, I'm going to put the point 2, 2. But on your parent, remember that you're looking for a vertical stretch, which means your x value is going to stay the same. But what would be the y value on your parent? Well, if the parent function is x cubed and you're replacing x with 2, then your parent function, that point that matches up with 2, 2 would really have been the point 2, 8. Okay, so on your parent, this corresponding point would have been at the point 2, 8. So now that you've been able to identify what the point is on the parent and what the point is on your new one, now we can kind of set this up algebraically. Where we are saying, well, 8 times a, okay, because I'm going for my parent, right? 8 times some value of a is going to equal 2. So I am going to go for my parent. Remember, you're taking the y value of your parent and you multiply it by an a value to get your new point. Well, we're just working a little bit backwards this time. And so we're given the kind of like alluding to the analysis that 8 is from the parent. So 8 times that vertical stretch or compression is going to give me 2. And so here I'm just going to divide by 8. And now I can find that my a value is actually 1/4, which makes sense because if we look at that, the parent function would be up here, and we ended up getting a little bit more compressed, a little bit smaller underneath that. So we could look at this and write g of x is equal to 1/4 f of x. That's one way that we can identify it. We can also say that g of x is 1/4, and remember f of x was just x cubed. So we can also say that. So just to make sure that this is also a way to write it in words, that g of x is a vertical compression of f of x by a factor of 1/4. So in words, this is what I would like you to be able to say. G of x is a vertical compression of f of x by a factor of 1/4.